Hey folks, welcome to Advent of Code in F#. We're at day 8 already. I am a bit late to the party today, I had a busy day. But let's see if we can knock out today's puzzle rather quickly. Day 8, Haunted Wasteland. You're still riding a camel across Desert Island when you spot a sandstorm quickly approaching. When you turn to warn the elf, she disappears before your eyes. To be fair, she had just finished warning you about ghosts a few minutes ago. One of the camel's pouches is labeled Maps. Sure enough, it's full of documents, or puzzle input, about how to navigate the desert. At least you're pretty sure that's what they are. One of the documents contains a list of left-right instructions, and the rest of the documents seem to describe some kind of network of labeled nodes. It seems like you're meant to use the left-right instructions to navigate the network. Okay. Perhaps if you have the camel follow the same instructions, you can escape the Haunted Wasteland. After examining the maps, two nodes stick out, AAA and ZZZ. You feel like AAA is where you are now. We feel like, okay? And you have to follow the left-right instructions until we reach ZZZ. This format defines each node of the network individually. Starting with AAA, you need to look up the next element based on the next left-right instruction. Okay, so we start at AAA, we look at the first instruction, which is an R. And we say what's to the right of AAA, therefore we need that line that says AAA. The right part is the right thing. Yeah, makes sense, makes sense. And by following the left-right instructions, we reach ZZZ in 2 steps. Okay, that's exactly the length of these instructions. But of course, we might not find ZZZ right away. If we run out of instructions, repeat the whole sequence as necessary. So keep repeating the instructions. That makes sense. For example, here's a situation that takes 6 steps to reach ZZZ. How is that the case? Oh yeah, it's only when we hit when we're at BBB and we have a right that we end up in ZZZ. 1, 2, 3. Yeah, that makes sense. Okay, so that's already a more interesting example. Yeah, that's already a more interesting example. Let's do that right away. This reminds me of a familiar kata, the Mars rover kata, which is almost the same, but there we're moving in a 2D grid instead of on a graph like we have here, but it's very, very similar. So I'm hoping to knock this one out rather quickly. Let's grab the example, or the second example, and let's grab our own input, which is bigger, a lot bigger, a lot bigger. So I'm gonna make a mental note that looking up the next turn, let's make that as fast as possible, or let's make that reasonably fast at least. Okay, first things first, we have a raw string or we have a raw text file, and we would like to parse it as always. So I'm going to parse our input into the list of commands or the list of instructions, and into the, what's the term for the map? So we have instructions, and we have nodes in the network, something like that. Yeah, okay. So let's define some types, which is a left or a right instruction. So we have instructions which are either left or right, and our full list of instructions is just a list of that. And then we have a list of, let's call them nodes, yeah, sure. And a node has a name or an identifier or something, and it has a, if you turn left here, if you turn right here. So let's model that. And let's call it the name. Everything is a string. We don't really care what's in there. And let's just have a left node and a right node, or the identifier of the left and right nodes. And let's define a map. No, let's not define a map just yet. Let's just start parsing using these types. So let's parse the example. Raw instructions is just the first line, and we can just parse a single instruction and put everything into a list. And we can write this parse instruction function. Pretty basic stuff, but it's good to warm up the fingers. So if it's the L character, we have a left command. If it's the R character, you have the R command. And in all other cases, we don't know what to do, so we crash. I feel like I've typed this exact parsing thing 100 times already. And given that I've been doing Advent of Code for a couple of years, that might actually not be an exaggeration. Okay, so we're parsing our instructions. Let's now also parse our map entries or our nodes. And that's example starting from 2 onward. So let's take the entire range starting from 2. It should start at A and end with Z, yes. And then we can just parse every line into its own node. Parse node. Which is a string like this, right? So we can split on. Actually, maybe this is the day. This is the day I will use a regular expression. Let's take a quick look at our input. Is it all triple character length or node identifiers? It appears so. So yeah, it's going to be an easy parse. I am willing to touch the regular expressions for today's puzzle. Where is it again? Yeah, pattern. Let's grab this. And let's replace this with stuff we want to match on. I'm gonna grab an example so I can play around with it. There we go. Okay, so how does regex stuff work again? Success false, interesting. How is this already not matching? Is it parentheses? Do we need to escape them? Yeah, success true. So we had to escape those parentheses. Okay, then we just want to match on whatever. What is this? String star, string plus. What's the one or more? Actually, we know it's 3 digits, right? 3 characters. What's the regular expression thing for a character? Actually, I don't really care. It's just... Yeah, no, I'm gonna have to look that up. I never use regexes, so let's take a quick look. Regular expression language, quick reference. That sounds relevant. A what? A bell character? I just want to match on whatever text. White space is not what we want. Non-word, word. Yeah, let's match on word characters. I think that's good enough. So word characters, and we want... Actually, we want to have 3 of them, right? So I think we can maybe do this. I see AAA in there, so I think we're capturing the groups correctly. So yeah, I think we're almost there. Let's see if we can capture some more groups. We still have a match. I see groups. I see triple A, triple B, which I think is correct. Okay, so let's extract the value out of this match and put it into our own type, the node type. So n dot, what is it, groups. Which one is it? I think it's the first group, should be our first captured group, yeah? 0 is the entire thing, is that how it works? Yeah, I think so. So this is our name. And then we have our left and our right, which are just these next groups in there. Left or right are the same in this example, but I think this is correct. Now we can just build our node. So yeah, I think we're parsing, and we're even using regular expressions. I am impressing myself today. Oh yeah, we need to get the value out there, and it's just a string, so that's all we need. Let's see if we can parse our input. I'm not a... Oh yeah, this can go, sorry. Some inline hard-coded data never works. So second to last is a B and left A, right C. That's correct. I'm happy. I think we're parsing correctly. So we have our instructions and we have our nodes. Sorry, I have an itchy throat. So I think we have everything we need to get started. Maybe let's do one more step. Our list of nodes is one thing, but we're going to do a lot of lookups, or potentially a lot of lookups. Let's make that a lookup table instead, or a map. A map, and if you do a map of a sequence, you need to have tuples, key value tuples. So let's map our nodes to the name of the node and whatever, the node, that's good enough. So now we have a lookup table that matches node names to the node itself. That will help us a little bit if we have to do a lot of lookups. So now we need to loop over, no, we're starting somewhere. So we're starting at AAA, and we want to keep going until we hit ZZZ. How will we do that? And we can use the instructions and we can repeat them forever until we hit ZZZ. So I think just a recursive call or a fancy stuff. Is it time for fancy stuff? Maybe it's time for fancy stuff. I feel like doing something fancy. The day has been stressful. The day has been less than stellar. So let's make today stellar. Let's play around with something we have not seen before. We have seen fold before, which is the functional for loop equivalent. Unfold is something, an interesting twist on a problem. Let's read the description here. Unfold returns a list that contains the elements generated by the given computation. The generator is repeatedly called to build the list until it returns none. The given initial state argument is passed to the generator. So an unfold is something that works in the reverse order, or the reverse direction of a fold. You start at something and you grow a list from that one thing. Whereas a fold, you have a list and you want to transform that into some kind of other state. Unfold goes the other way. So we could use an unfold to generate a sequence of locations where our camel is traveling, and we can just like traverse that list that we generate until we find our first ZZZ, which is the finish line. So that's my approach. I'm going to try to generate a list of all the locations we visit given the instructions we have and the node map. And then let's just go over that list until we hit the ZZZ. That is the plan. So we have a generator and an initial state. And I'm gonna just take AAA as the initial state, and we need a bit more. So I'm gonna just make a type state, which is our current location, which is our node name, but it's just a string. And what we also need is like what's the next instruction we have to take. So I'm just going to take a sequence of instructions so we know what to do next. And I'm saying sequence of instructions because I'm scheming. I'm going to go all the way with crazy stuff today. Unfolding is something we have not seen, and I'm going to do this instructions thing that keeps repeating. I'm gonna try to do that with an infinite list or an infinite sequence. So that's part 2 of the craziness today. Let's try to do that first because we're going to need that first. If you look at this, the raw parsed instructions are just 3 elements long. Let's build on that. Let's make a looping instructions. And that's just an infinite sequence. And if you look at init infinite, it gives you an initializer, which takes an integer and returns a sequence of t's. But actually, no, let's not do it. Let's do it something else. I think maybe init infinite would work. So what does init infinite take? It takes an initializer function, and it returns an element in the sequence. So if we just say like, it takes an initializer function and it returns our instructions, it does not even look at the index it's given. Now, if you look at what's going out, instruction is not defined. Come on. Okay. So if you look at the type of this thing now, it's an instruction list sequence. So it's a sequence of a list of instructions. That's too much. We only need to have one collection type. So if we flatten this list again by doing a collect ID, that's something we've done already. If you look at the type now, it's a sequence of instructions and it's an infinite sequence. That's the important twist. So if we execute this and if we say take the first 10 elements of this sequence, you see that it starts to repeat. Let's maybe even to list it to make it really clear. It's left, left, right, left, left, right, left, left, right, and it keeps on going. But it's an infinite list. So that was crazy stuff. Part 1, we have our looping instructions, and we used infinite sequences. Let's go back to part 2 of the crazy stuff, our unfolding, right? So our initial state is just we start at start. So let's grab these. Let's grab these. So we start at start and our instructions are just the initial looping instructions. And now let's generate all the possible or the entire sequence of nodes our camel will traverse. What was generator again? A function that takes a state and it returns a tuple of an element and a new state. Yeah. Why is my squiggly saying that it's not okay? Oh, was there some kind of option thing in there? Yeah, it has to return an option if you want to continue. And seeing that it's not infinite. We could hold the unfolding, or we could hold or once we see the ZZZ in there. Yeah, when our location is ZZZ, we don't need to continue on. So we can do something with this option as well. Okay, so this is the type signatures. They look correct. Now let's make it let's make it do actual stuff, right? So instead of the initial location, let's feed this the initial state variable or the state type that we declared here, the record. Okay, so what do we need to do? We need to look up We are right now at location, and we need to look up our next location. So state.location. We need to look that up in our map, and our map is called nodes here. So let's just use that. So that's the next node we need to take a look at. And then we need to know our next location, our next instruction. And that's state.instructions, first element, so the head of the sequence. And let's match on that. If it's a left, we take node.left. If it's a right, we take node.right, of course. And that's a string, so that's the node identifier or the node name for the next one. Okay, so we have the next node, and I would say if the next node, or yeah, that's okay. If the next node is something we can return, because we just want the sequence of nodes. And state, we need to update state a bit because, yeah, we moved. So next state is state with location changed, but also the instructions changed, right? So we consumed one instruction here, and all the rest of the instructions is the tail, so everything except the head. And we can pipe state into the return. Why are there so many squiggly lines? This copy and update record expression changes all fields of state. Consider using record constructor syntax. Is that faster? Is the update statement slower? Why would it suggest this? This seems more like refactor or design friendly if there's a new... it's a trade-off. Both are possible. I was thinking if there's like a new field in this record, then this update statement will work. And if you don't do the with thing, it'll break. But maybe that's what you want if you introduce a new record. It all depends. Software is one big all depends. But good engineers know what it depends on. So it depends is a bad answer if people ask you a question. You have to specify what it depends on and what in this context might be the best move. But we are digressing. I was thinking, I think this might work. Let's maybe play around with it before I proceed my train of thought. Did I just force my computer into an infinite loop? I think I did. Let's stop that. Oh yeah, I'm doing list.unfold. I think that's never a good idea if you're building infinite sequences. So let's call this path. So I changed list.unfold to sequence.unfold to stay in the lazy evaluation world. Yeah, so let's take a couple of steps here. It's doing something. It's doing something. But it's saying BBB. I'm not seeing the first state, so yeah. It's not very super clean. We're skipping the initial state, stuff like that. Actually, we could do that. We could do that, right? We could return state.location here. And I think that actually might help us with the end condition as well. So yeah, maybe that's a good idea. We know that we should end up at ZZZ sometime soon, right? Why am I not seeing ZZZ after 6 steps? Probably because we have a bug. Oh no. Oh yeah, that's the first one. So it's 1, 2, 3, 4, 5, 6. Yeah, I think we're there. Let's maybe have the sequence generation stop because we have this something. I think we might be able to make it work. If our current location is ZZZ, we can just break out. Where is our end? Finish. So if we are at the finish, we stop. We stop working, and otherwise we do the thing we said we were, or we already implemented. Let's take a look at this one. Nope. The input sequence has an insufficient number. Okay, that's interesting. That's actually exactly what we want. What is it? 5, 6? I think it. Oh, we're almost there. No, so it's not returning the. Oh yeah. We're so close. Yeah, we're so close. Let's get rid of this if. We're almost there to do the thing I think we want to do. So this is correct, but if next state, so we have next node. Actually, never mind. We're making this way harder. I think we are very close to what I was trying to do. But I'll have a think on it later. I just want to solve my puzzle first. What's the problem right now? What did we break? Formatting again, of course. Yeah, let's take a quick breather and let's have this thing working first before I try to clean it up. So this looks correct. We're taking 7 because we put the initial location in there. So we're taking 6 steps and we see ZZZ. So I think I could actually do take while or skip. No, take while. I think this will solve the problem for us. There we go. So we're seeing a 6. So length to finish is this thing. We're just taking nodes in the path until we see our ZZZ, and that's the amount of steps we're taking. And it's 6, so I'm pretty comfortable that it's correct for the example. Let's make sure. Let's try it for our input as well. So I'm inlining everything here. Where are we parsing our nodes? Here and here. I'm gonna write a quick parser function around that. So we can play around with different kinds of inputs. So parse input needs to return nodes and instructions or looping instructions. Let's have it return looping instructions, sure. So this returns our looping instructions and our nodes. And it uses the input variable instead of example, and that was a list of strings. There we go, and then we can use that right here. Instructions nodes equals parse input. Instruction sequence and our nodes, so that's our map, yeah. Okay, our generator function needs the nodes, but let's pipe them in. It was a bit dirty to reference them in the global scope here anyway. And this is our solving function, so I'm gonna put all this thing here, put all this thing here, plug in map. I'm taking way too big a step. I would tell the colleague I would be pairing with right now, like, take smaller steps, please. Learn to run before you, or learn to walk before you run. And I never heed my own advice. Parsing already loops, right? Yeah, parsing already loops. generator itself is the function. And generator itself should take the nodes as well, because we pipe them in. So everything is local state. There we go. There we go. Everything compiles again. I think we can run our solve on the example and 6 should come out. There we go. And if we run it for our input, we get nothing because it's a lot of work. I was expecting it to be a bit slower. I was not expecting it to be very extremely slow. Interesting. Let's put some timings on. I hear my laptop take flight, so it's doing something. Do we want to print out some kind of progress indicator? What could we do for a progress indicator? I think if you print out like every iteration, we're going to see a lot of things. So yeah, I'm just gonna start it and run. I was hoping to get done in 30 minutes today. We are 30 minutes in right now, and we are not. So here's what I'll do. I'll let this run for a minute or two and hope that something comes out. But if part 1 is already number crunchingly difficult, then I fear for part 2. And while this is running, let's have a think on the problem. What can we exploit? We can exploit the fact that we're doing loopy loops. We can't really improve very much on our lookups. That's like a logarithmic access, looking up stuff in the map, so that's good, not great, but I was thinking maybe we can memoize it, but memoizing or keeping results you've already seen will not help really that much for a singular lookup, so that's not the fix we can use. What's the fix we can use? Let's take a look at our input. Why is it crunching numbers this badly? Because we have 700 nodes with a lot of dancing around, probably. Or we have a bug. That's also possible, of course. We only saw the 1.6 come out of the end. Yeah, I'm not sure on how to proceed. I'm gonna have my computer work on this for a minute or two more, and then I'm going to revisit my approach here. If this even for part 1 provides to be a challenge, I'm very curious about the part 2 twist if and when we get there. But I think I'm gonna cut the stream here, or I'm gonna cut the recording here, and hopefully this cranks out the number, and I will get back to you for part 2. And otherwise, let's revisit part 1. A man's gotta do what a man's gotta do while solving Advent of Code. I hope you enjoyed today's video, and I would like to see you again on Advent of Code in F#. Bye bye.